Imagine a world where the human brain and computers are seamlessly connected. A world where paralysis is no longer a barrier, where memories can be stored and replayed, and where artificial intelligence doesn't just exist beside us, but within us. This isn't the stuff of science fiction anymore. It's the ambitious vision of Elon Musk's Neuralink. Today, we're diving deep into the revolutionary technology behind Neuralink's brain chip. We'll uncover how it works, the groundbreaking science behind it, and the ethical debates surrounding its use. But here's the twist. By the end of this video, you'll learn not just how Neuralink might change medicine, but how it could redefine what it means to be human. Intrigued? Let's begin. The vision of Neuralink. To understand Neuralink, we first need to understand the mind behind it. Elon Musk, the man who brought us Tesla and SpaceX, has a knack for turning audacious dreams into reality. But Neuralink might be his most daring project yet. In Musk's words, Neuralink's ultimate goal is to achieve a symbiosis with artificial intelligence. At its core, Neuralink enhances human potential by creating a direct interface between the brain and machines. But what does that actually mean? Let's break it down. The science of the brain-computer interface, BCI. Our brains are an intricate network of neurons, about 86 billion of them, that communicate through tiny electrical signals. Everything you think, feel, or do originates from these signals. Now, what if we could decode them? That's where brain-computer interfaces, or BCIs, come in. BCIs are devices that translate brain activity into digital signals. Neuralink's brain chip takes this concept to a whole new level. Using ultra-thin electrodes, the chip connects directly to neurons, allowing it to both read and influence brain activity. Think of it as a bridge, a two-way communication channel between your brain and a computer. Let's dive deeper into how these neurons communicate. When a neuron fires, it creates an action potential, a tiny electrical impulse that travels along the cell membrane. This impulse triggers the release of neurotransmitters, chemical messengers that bridge the gap, synapse, between neurons. BCIs work by detecting these electrical patterns, essentially eavesdropping on the brain's natural communication system. The challenge lies in the complexity of neural signals. Unlike binary computer code, neural communication is analog, with subtle variations in timing, intensity, and pattern. Traditional BCIs often struggled with this complexity, only able to detect broad patterns of brain activity. But Neuralink's approach is revolutionary in its precision. The company has developed what they call neural lace technology, a mesh of incredibly fine threads, each thinner than a human hair. Each thread contains multiple electrodes that can both record neural activity and stimulate neurons. What makes this technology groundbreaking is its scale. While traditional BCIs might use dozens of electrodes, Neuralink's device incorporates thousands of them. These electrodes are made from materials specifically chosen for their biocompatibility and durability. The threads themselves are flexible, allowing them to move with the brain's natural motion without causing damage. This is crucial because the brain isn't static. It pulsates with your heartbeat and can shift slightly with movement. The signal processing involved is equally sophisticated. Raw neural signals are incredibly noisy, filled with background activity from thousands of nearby neurons. Neuralink's system uses advanced algorithms to filter this noise and identify meaningful patterns. Machine learning plays a crucial role here, helping to interpret which neural patterns correspond to specific thoughts or intended actions. But perhaps most impressive is the system's ability to achieve two-way communication. Not only can it read neural signals, but it can also write them. This means the device can potentially restore lost neural connections by artificially recreating the signals that would normally flow between different parts of the brain. The technical challenges of creating such a system are immense. The brain's environment is incredibly hostile to foreign objects. It can form scar tissue around implants, degrading their effectiveness over time. Neuralink has had to develop special coating materials and insertion techniques to minimize this immune response. Power management presents another crucial challenge. The device needs to operate continuously while consuming minimal power and generating minimal heat. Neuralink's solution involves wireless charging and data transmission, eliminating the need for physical connections through the skull. Temperature regulation is also critical. The brain is extremely sensitive to temperature changes, so the device must dissipate heat effectively while operating. Neuralink has developed sophisticated thermal management systems to ensure the device's operation doesn't affect surrounding tissue. The spatial precision of the system is remarkable. Each electrode can monitor or stimulate a very small cluster of neurons, allowing for incredibly detailed control. This precision is what makes it possible to target specific brain functions or restore particular neural pathways that have been damaged by injury or disease. How Neuralink works. Neuralink's brain chip is built to be minimally invasive. The procedure to implant it is done by a robotic surgeon designed for precision and safety. This robot places the electrodes in the exact locations needed to interface with neural circuits. But let's delve deeper into the fascinating process and components that make this possible. The implantation procedure itself is a marvel of robotics and precision engineering. The surgical robot, which looks somewhat like a high-tech sewing machine, uses advanced computer vision and real-time brain mapping to navigate. It can detect and avoid blood vessels during insertion, significantly reducing the risk of surgical complications. Each electrode thread is individually inserted with micron-level precision, which is about 1/100th the width of a human hair. The main device, often called the link, consists of several key components. At its heart is a custom ASIC application-specific integrated circuit chip that processes neural signals in real time. This chip contains over 1,000 channels of signal processing capability, each able to monitor multiple neurons simultaneously. The device's outer shell is made from biocompatible materials that have been extensively tested for long-term compatibility with brain tissue. Power management is one of the most innovative aspects of the system. The device uses inductive charging, similar to wireless phone charging but far more sophisticated. A compact external charger can be worn over the implant site, keeping the internal battery topped up without any physical connection. This wireless charging system has been carefully designed to prevent tissue heating, using precise frequency control and power management algorithms. Data transmission is equally impressive. The Link uses a custom-designed wireless protocol to transmit neural data to external devices. This protocol has been optimized for extremely low latency. We're talking milliseconds here, while maintaining high bandwidth capabilities. The system can transmit massive amounts of neural data in real time, essential for applications like controlling prosthetic limbs or interfacing with computers. The electrodes themselves deserve special attention. Each thread contains multiple recording sites along its length, allowing it to monitor different layers of the brain simultaneously. The threads are coated with special materials that help them slide into place without causing damage and promote stable, long-term recording. This is crucial because the quality of neural recordings tends to degrade over time with traditional electrodes. Signal processing happens in multiple stages. First, the raw neural signals are amplified and digitized right at the recording site. Then, sophisticated filtering algorithms remove noise and artifacts. Machine learning algorithms running on the chip identify specific patterns of neural activity in real time. This processed data is then transmitted wirelessly to external devices, where more complex analysis can occur. The companion app that receives this data is equally sophisticated. It can translate neural signals into commands for external devices, whether that's moving a cursor on a screen or controlling a robotic arm. The app also provides feedback to help users learn to control the system more effectively, creating a dynamic learning loop between the brain and the interface. Maintenance and updates are handled wirelessly too. The system can receive software updates to improve its performance or add new capabilities, much like a smartphone. This means the device's capabilities can continue to evolve even after implantation, adapting to new use cases and improved algorithms. Safety features are built into every level of the system. Multiple redundant sensors monitor the device's temperature and operation. If any anomalies are detected, the system can automatically adjust its operation or shut down to prevent any potential harm. The device is also designed to be removable if necessary, though the goal is for it to function reliably for many years. The scalability of the system is perhaps one of its most impressive features. While current versions focus on specific brain regions, the architecture is designed to support multiple implants working together, potentially covering larger areas of the brain and enabling more complex applications. The present-day applications. Let's start with what Neuralink has already achieved. In 2020, Neuralink demonstrated its technology in a pig named Gertrude. The chip implanted in her brain was able to track neural activity in real time, showing how specific brain signals correspond to actions. This wasn't just a simple demonstration, it provided crucial data about long-term biocompatibility and the stability of neural recordings. Then came a monkey named Pager. In 2021, Neuralink revealed a jaw-dropping experiment where Pager played Pong using only its mind. The chip decoded Pager's brain activity, allowing him to control the game with no physical input. But what made this demonstration particularly significant was the speed and precision of control. Pager learned to play the game better with his mind than he had with a joystick. More recently, Neuralink has begun human clinical trials, marking a crucial milestone in its development. These trials focus on individuals with quadriplegia and other forms of paralysis, aiming to restore their ability to interact with digital devices through thought alone. The initial results have shown promising outcomes in helping patients control computer cursors and type text. For paralysis patients, Neuralink's technology offers unprecedented possibilities. The system can decode intended movements from the motor cortex, bypassing damaged spinal connections to control external devices. This means a person with complete paralysis could potentially operate a smartphone, control a wheelchair, or even guide a robotic arm with their thoughts alone. In the field of communication disorders, Neuralink shows enormous potential. For patients with ALS or locked-in syndrome, who retain full cognitive function but cannot speak or move, the technology could restore their ability to communicate. Early trials have demonstrated that users can type at speeds approaching 20 words per minute using only their thoughts, a dramatic improvement over existing assistive technologies. The technology is also showing promise in treating neurological conditions. For epilepsy patients, the system can potentially detect the onset of seizures before they occur and deliver targeted stimulation to prevent them. This real-time monitoring and intervention capability could revolutionize how we manage neurological disorders. Vision restoration is another active area of development. By interfacing with the visual cortex, Neuralink's technology could potentially restore basic sight to individuals with certain forms of blindness. Early experiments have successfully demonstrated the ability to create simple visual percepts, or phosphenes, by stimulating specific areas of the visual cortex. In the realm of mental health, researchers are exploring how Neuralink's precise neural monitoring could help treat conditions like severe depression and anxiety. By understanding the neural patterns associated with these conditions, the technology could potentially deliver targeted neuromodulation therapy more effectively than current treatments. Pain management is yet another promising application. The device's ability to modulate neural activity could offer new ways to treat chronic pain conditions without the risks associated with traditional pain medications. Early research suggests that precise neural stimulation could interrupt pain signals before they reach consciousness. The system's capability to record vast amounts of neural data is also advancing our understanding of the brain itself. Researchers are using this technology to study how different brain regions communicate, how memories are formed and recalled, and how decisions are made at the neural level. This research could lead to breakthroughs in treating neurodegenerative diseases like Alzheimer's and Parkinson's. For stroke rehabilitation, Neuralink's technology shows the potential to help patients regain lost functions. By creating artificial bridges across damaged brain areas, the system could help restore movement and speech capabilities more effectively than traditional rehabilitation methods. Perhaps most remarkably, all these applications are just the beginning. As technology continues to evolve and our understanding of the brain improves, new applications are being discovered and developed. The real-time nature of the system means that treatments can be continuously adjusted and optimized for each patient's specific needs. The ethical dilemma. As promising as it sounds, Neuralink isn't without controversy. Critics have raised valid concerns about the ethics of merging humans with machines. For example, who controls the data collected by the chip? Could the technology be hacked, leading to unimaginable consequences? And what happens when such enhancements are available only to the wealthy, widening social inequality? These questions highlight the need for strict regulations and ethical guidelines as the technology progresses, but they also force us to confront deeper philosophical issues. If Neuralink allows us to alter our brains, what happens to our individuality? Our humanity? The future of Neuralink. Looking ahead, Neuralink's potential extends far beyond medical applications. Musk envisions a world where humans can upload and download memories, access the internet with a thought, and even preserve consciousness after death. While these ideas sound like science fiction, they're rooted in the same principles that make Neuralink work today. The road to this future won't be easy. It will require breakthroughs in neuroscience, computing, and ethics. But if history has taught us anything, it's that human ingenuity has a way of making the impossible possible. The human-AI symbiosis. Neuralink represents a bold leap into the unknown. It challenges us to rethink the boundaries of technology, medicine, and even our humanity. Whether it becomes the key to curing diseases or the foundation for a new era of human evolution, one thing is certain: Neuralink is a glimpse into the future we're building together. So what do you think? Are we ready to embrace this brave new world, or are we venturing too far, too fast? Share your thoughts in the comments below. If you found this video insightful, don't forget to like, share, and subscribe for more deep dives into the science shaping our future. And if you want to stay ahead of the curve, hit the notification bell so you never miss an update. Together, let's explore the frontiers of human potential. Thanks for watching, and we'll see you in the next one.